to bring everything together, I have here this transform fish object, which Mesh has in its displacement node editor this setup you can see here. So basically the setup is I'm transforming the point positions of the fish, but just on the x-axis. So when I connect the vector into a scalar port, basically what's automatically done by me is that only the x channel is used. So I don't have to worry because everything I'm using is the x channel, so I don't have to worry about being explicit on the conversion from vector channels to single scalar channel. So I'm using the fish point positions, and I'm going to use this object A position and scale to drive the two main transformations, scaling and translation. And I'm going to also use this object here. I'm also using this object called reference to decide where's the pivot for the scaling. So if I put, say, the reference object here, and now I scale, you can see that the scaling will happen around that position. Or let's say that I move this here to the tip of the jaw, and you can see that now it happens around the mouth. So this is what the center input does. And lastly, I have here this input to reflect it. So let's look at all of the operations. So to start off, I have the value, the scalar value that I want to transform, and it's plugged into a pass node. A pass node is basically, I don't have a pass through in Lightwave. So basically, what I usually do, I get an add node and I rename it to whatever I need. So in this case, I just call it pass. So it's passing this value because it's going into two places. So whenever I have a flow that goes into more than one place, usually I have an intermediary node. And so in this case, I just renamed an add node to pass. And so first, this scalar value goes into the chain of transformations. And lastly, it goes here where it says delta. So what is it doing? Well, basically it's comparing the result to the initial value. So this is basically my end value after all the transformations minus my initial value. And this is the reason that this is what is connected here in the displacement is because displacement takes, it happens as an addition to the mesh. You have a base mesh, it's like a relative morph, just like I've mentioned here with the position delta. So basically when you apply something here in the displacement, it expects that you're adding that to whatever you already have. So it means that my base mesh is my context. And so whatever I put in here, I have to put it in the context of my base mesh. Of course, if I use my base mesh itself to perform some calculations, in this case to transform those positions, then I have to take it out, take that initial value out, because you'll see that if I apply my point positions to the displacement, you'll see that I'll have some change already, and I don't want that. So I have to take it out, the influence of the initial value. So I get basically, instead of, let's say that I have the origin here, and I don't want the world position that goes from the origin to my end results after all these transformations, I want the position that goes from my initial position to my end position. And that's why I have here this subtract node and the output called delta, which is useful for this particular case. Then after that, I have the center value being subtracted. So here I'm putting the values in the context of the center value. So the center value goes into two places, into this subtract node and into this add node. So it's that thing that talked about conjugation, where you apply an operation and the inverse of it in the beginning and in the end. So in between, I've created a space where whatever I do in there, it's in a different context. So this is what I've done here. I have add and subtract bracketing in a way that different context, and that's why I have here the pass, just because it goes into two places. Then in the middle of the subtract and add, I have the actual geometric transformation operation. So I have first scaling, then I have translation, and lastly I have reflection. This order, multiply and add, or scaling and translation, is very standard. The thing that is not very standard that I decided to do was to put the reflection after the translation. So usually reflection is here after or before the scaling. So it's actually like a special case of scaling. But so I decided, if I just want to do that, I could just flip the sign on my input. I can just, let's say put sign scale, and I can just do this if I want to have something to be flipped like in the standard way. So I'd say, well, let's do something different. Let me put the reflection, after the translation, but also before I put things back. So it uses the center that I define. So this is a bit non-standard, the reflection here, but the multiply and the add are very standard. So first you scale and then you translate. First you solve anything that is relative or pivots around the origin, right? You'll have that you have that with scaling and also with rotations. They solve around the origin. And afterwards, you move that system. After you've solved those things around the origin, you move it away, you apply the translation. So that's why you do, so usually in Lightwave, you see position, rotation, and scaling, but actually the order, in this case, I'm going to call it translation. Actually, the order of evaluation is scaling, then rotation, and then translation. And these two revolve around the origin. So in this case, I'm just doing scaling and translation. So first multiplication, then addition, and that's what I have here. And we can see why that would be strange if I did the other way around. So let's see, scale, multiply, and add, scalar, add. Okay, so I'm gonna pop two of these. And I'm going to change the order. And so this one is going to be standard. This is going to be non-standard. And of course, you're in the node editor. You have freedom to do whatever you want. Just trying to explain this standard here. And let me put the position into the add nodes and the scaling into the multiply nodes. Now, lastly, I have to do the delta by myself. Here I have the delta done internally, so I have to do it here outside by myself. So scalar subtract, and I have to subtract the initial position. And so when I put this here, you can see that I still maintain the same type of result. So when I do a scaling and I move, it seems like the scaling is around the position that I decided for the object. But if I do the other way around, if I translate first and I scale afterwards, what will happen is that as I move, let's see, scale something, I've put the position on the multiply. So wrong connections there. Okay, so when I move the fish and then I scale it, you see that the scaling still happens around the origin. But because, since it's done afterwards, it's going to look like this. So it's not going to look so good because you suddenly have the object flipping around and not apparently around the position where it was put. So like this. Right, so let me delete this and let me talk about the inverse operation. So this is the order. This is very standard, multiply and add. And what if I want to do the inverse of this? What if I want, instead of having multiply and add, I want to unwind or do the inverse operation? So I've mentioned the inverse operations, subtract and divide, but does it mean that if the order here is to multiply and then add, does it mean that I just have to invert the operations to do divide and then subtract? Well, actually, no. This is wrong because it actually is a bit more like the Matryoshka doll, the Russian doll I've shown here. So here, the first doll that I opened is also the last doll that I closed. Here in this maze. In these steps, also the first action that you've done is also the last one you do in the inverse manner. So this means that if I went in this way to do this transformation, I have to go the other way to do the inverse action. And I do not only inverse the operations themselves, but I also invert the order by which I do them. So first I'm going to subtract, and then I'm going to divide. So from left to right, I'm going to subtract, and then I'm going to divide. And this is the inversion of multiplying and then adding. So not only are the operations are inverted, the order is also inverted. And so this is why here in this other compound called transform1d inv as for inverse, I can see that first I have subtract and then I have divide. The order is very similar, so let's recap here. First, I take the center in consideration, I scale, I translate, I reflect, then I put back the center, and then lastly I do my delta. Here in the inverse version, I still take the center in consideration first. So I still have to do the same thing, put my values in the context of the center. Then I do reflection first, then I do subtraction, so the translation, and then I do the scaling with divide. So reflection, translation, scaling, while here I had scaling, translation, reflection. And so to prove that it's actually doing the inverse action or is unwinding, I can actually apply both. So I can apply this one and then apply this one. So let's see, I'm going to apply scale, position in translate, scaling in scale, and the position in center. Right, and now since the delta is done from the initial position, I cannot apply this delta here. I have to do my own delta. So in this case, I'm just going to reuse this subtract node and apply the result in here. Okay, so now as you can see, as I move this, nothing happens. And the question is, well, why it doesn't happen? Well, because I have a value and I applied an operation and then I applied its inverse operation. So basically what I get back, since these two annul each other, I get back my value. So apparently, nothing happens. And when you have this, it's a good confirmation that you're doing the inverse operation. It means that you're unwinding or you're undoing the thing that you did before. So as I move and scale, see, nothing goes on. Of course, if I just connect the delta of this one here, you see that there's actually something going on at this step. So I'm actually transforming the fish in a way. This concludes the introduction to simple geometric transformations, their sequence, and how to invert them. It's going to be a topic that's going to be further developed when I get into 3D vectors. Next, I'm going to look into mapping, how to control ranges of values, how to do conversions, how to ease values. And this sequence of geometric transformation is the first example. Cheers.